to Digital Electronics EEE 301 FlipFlop and Latches. This is the second part of the lecture. Okay, so now let me use the laser pointer again. So we are in this situation when S equals 0, R equals 0. So we already considered S equals 1, R equals 1. We got Q equals 0, Q prime 0. So Q 0, Q prime 0. Now for the next state, S equals 0, R equals 0. So when our S 0, R 0. So what will be the output Q and Q dash? So if we start from this one, okay, so now we are starting this one, but you can start with this one again, which we discussed here. Okay, so just consider for this one. So S0 and our previous value was Q was 0. Just look at here. Q was here, Q was 0. So this 0 0. So this 0 comes here. So this 0 and this 0 0 0. So if input 0 0, output is 1. So this becomes 1 now. So this is your 1. So our Q prime becomes 1. So Q prime becomes 1. And this one goes here, right? So this 1 and 0 0 1. So 0 1 becomes 0. So your Q becomes 0. So now for S equals 0, R equals 0, Q becomes 0, Q prime becomes 1. But if we start with this one, what happens if we start with this one? Just look at here again. So consider our Q equals here, Q equals 0, Q prime equals 0. So Q 0, Q prime 0. So and now for if you look at here, for S equals 0, R equals 0, for the same state, so L0, R0. So if you start with this gate, so we had R equals 0 and previously you have 0 here, Q0. So these zeros goes here, so 0 0. So 0 0 becomes 1. So this output becomes 1. This one comes here, 1 0. So 1 0 becomes 0. So this becomes below. Now your Q changes to 1 and 0. So previously it was 0 and 1. Now it changes to 1 and 0. So this is basically unstable state. This is the unstable state because for case 3, for S equals 0, R equals 0, we got Q equals 0, 1, and also we got 1 0. So this is unstable state. So for NOR SR latch, so this is the summary what we discussed already, case 1, case 2 and case 3. So we have invalid state for these situations. So this is for 1 situation, S equals 1, R equals 1, not used. And if 0 0, this is called memory. 0 1, we got 0 1, 1 0, we got 1 0, and for 1 1, this is not used. So I suggest you try to do the same thing for NAND SR latch. So this is your NOR SR latch, this is the truth table. For NAND SR latch, the circuit will be look like this, and if you follow the procedure like case 1 to case 3, you will find this kind of truth table. So for 0 0, you got here memory. For 1 1, not changed. So here it got inverted. For 0 0, not used, just like here, not used. For 1 1, for 1 1, got 0 0 value, so memory. For 0 1, it got 1 0. For 1 0, it's getting 0 1. It's kind of inversion. So this is your assignment. So I suggest you try to do it by yourself. Gated SLH. So you can say uh, this is your SL latch. This is your enable pin with 2 NAND gate. So SL latch, enable pin, and 2 NAND gate. All of this will produce that gated SL latch. That means it has kind of gate which is your EN. So this is the typical block diagram here. So you have S, R, enable pin, Q, and Q prime. So now For gated SL latch, the output changes when En is high. So when your En is high, then the output will change. And we need to determine under what condition the invalid state occur as well. And if you look at the characteristics tables here, so this is only changing state when En is 1. So En is 1, then Qt is your present state, Qt plus 1 is your next state, S and R is your input. So if your initial S and R is 0, 0, so for a 0, 0, no change. So output will be no change means previous value. So your previous value is 0, so next value is uh, no change means 0. For 0, 1, for 0, 1 it is reset to 0, it's resetting to 0. For 1, 0, for 1, 0 it is set to 1. So 1, 0 set to 1, and for 1, 1, so 1, 1 is intermediate state. So this is when your present state is 0. For the second portion, if your present state is 1, in that case, if your SR is 0, 0, 0, 0 means no change. So previously you have 1, so that will be continuing as 1. 0, 1 means reset, so reset to 0. 1, 0, 1, 0 means set, so set to 1. Then 1, 1 intermediate, that this is intermediate state. So this is your characteristics equation. So if you draw the K-map for this one, Qt plus 1, and for S and R, so you will find this kind of equation. So this is Qt plus 1 equals SR and Q. This is Q is for Qt. So you can simplify your K-map and you will find this kind of equation. Now get a D-latch. So the difference, the D-latch with the previous one is like here, instead of R, so you have the input which is inverted one. So this becomes inverted. So make R input equal to S prime for gated D-latch. So previous your this was is S, this was is R. So now if you just invert it and connect it here, then it can produce D-latch. And other thing is same as the previous one. You also have the enable pin as well. So this is the typical block diagram. So instead of having two input, right now you have only one input, D. Okay, so the D latch eliminates the undesirable condition of invalid state in SR latch. So if you remember previous one, we had for one on state invalid condition or undesirable condition. So we can eliminate that undesirable condition here. Just now look at here. So this is also working when our EN is high, so enable pin is high. Then if T is high, the latch is set. When En is high and if T is low, then latch is reset. Hence, when En is high, Q follows the data D values, right? Just look at here. So the characteristics table. So this is your En, and this is your input D, and this is your output or next state, you can say. So when your En is high and your D is 0, the output will be reset. When your En is 1 and D is 1, output will be set. So whatever value you are giving as the input, you are getting the same value as the output. So this is your D latches. And when your En is 0, that means it doesn't really matter whether D is 0 or 1. It will not work. So no change. And if you draw the KMF for these three, this one, this one, and this one, and simplify it, you will find it for En1, Q of T plus 1 equals T. That means whatever value you have as the input, you will get it as the output. So next step. So now we will know about when latch circuit is not suitable. Okay, so let me use the laser pointer again. So our latch circuit are not suitable in synchronous logic circuit. So that means if the logic circuit is synchronous in that case our latch is not suitable. So we need to do some kind of arrangement so that we can use a latch or similar kind of flip-flop in synchronous logic circuit. The problem is when the enable signal is active, the excitation input are gated directly to the output. Thus, any change in the excitation input immediately causes a change in the latch output. So, whatever value you're giving as an input, immediately it goes to the output. So, this creates a problem, especially for synchronous circuits. The problem is solved by using a special timing control signal called a clock. So, using a clock, we can eliminate this kind of situations to restrict the times at which the state of memory elements may change. This leads us the edge triggered memory elements called flip-flop. So in flip-flop this kind of problem is actually solved. So now we'll discuss about the flip-flop. Basically edge triggered flip-flop. So flip-flops are synchronous bistable device. The output changes state at a specified point on a triggering input called clock. Change state either at the positive edge or at the negative edge. Positive edge means rising edge, negative edge means falling edge of the clock signal. So what does it say? So this is basically our clock signal, like high low, something like that. So if you go from low to high, so this one is called positive edge. If you are going from again low to high, this is your positive edge. But if you're going from high to low, so this transition is called negative edge, same as it's high to low. So this transition is negative edge. So whenever we have a clock and due to this positive edge or negative edge, our state will be changed in the flip-flop. So previous problem can be solved in this flip-flop. So now look at here. So this is couple of diagram for SRD JK trigger flip-flop, and remember this sign, this symbol represents the clock input. So say like here, this is your SR flip-flop, so and this is your clock. So this represents the clock signal, right? This kind of sign, and this is your D flip-flop. This is your JK flip-flops. All of them have clock. But remember, all of them are positive edge clock. That means they will activate at positive edge. And if you look at the bottom part, so they are called negative edge, because if you look at here, this clock is actually here there is a bubble. So that's the difference. That means all of these flip-flop work is negative edge. So now look at the SR flip-flop. So on the triggering edge of the clock pulse, that means it could be positive edge or negative edge. If your S is high, S high means your R low, and S high means set state. R high means reset state. Obviously, in that case your S is low. And if both input low, there will be no change. And if both input high, and this is the invalid state. So this is the basically characteristics table of positive edge triggered SR flip-flop. So if you look at here, so there is no clock, that means there will be no change whatever you have the value of S and R. But when there is a clock, remember this is positive edge clock. If negative edge, it will be downwards sign, and upward sign is for positive edge triggered clock. So if your R is high, that means reset. If your S is high, that means set. And other is zero. Like this one zero, this one zero. If both is high, invalid. If both is low, that means no change. X represents don't care here. So our SR flip-flop, it consists of three parts. These are one basic NAND latch, another one is a pulse steering circuit, and the last one is pulse transition detector or edge detector circuit. So the pulse transition detector detects a rising or falling edge